Welcome to Tetryonics. In this lecture we'll be covering the quantum geometry of electricity. This lecture forms part of the series based on Tetryonics Book 1, Quantum Mechanics, and more in depth on the Tetryonics Book 2, Quantum Electrodynamics. Both of these books are available on YouTube and on Google+. Quantum electrodynamics itself refers to the motion of charged bodies in a region. All energy and/or its mass equivalence is simply the result of equilateral energy geometries within any region of space and time, be it in the form of heat, fire or light, or even in the form of matter itself. Equilateral energy geometries come together to form square quantas of energy, and it is these square quanta of energy that forms the backbone of all our mass-energy-matter relationships. And accordingly, in recent times, we've begun to use our knowledge of electricity and of energy storage to be able to store work, generate work, and move these stored energies from one point to another in order to do work. Tetryonics will show the exact quantum relationships of equilateral energy to their energy momenta and their charged masses, and how these energies can be stored or created and stored in any region or any medium in order to do work on charged matter geometries. It's this work on charged matter that forms the basis of electricity in our modern technology. Tetryonics itself, as you can see there on the bottom right, relates to equilateral energy momenta. These momenta come together in a way to produce square energy geometries. The square energy geometries themselves are equilateral in all cases, be they the quanta or the scalar energy that they produce by coming together. In this case, you can see the three sides of the equilateral energy triangle, the scalar energy, are marked with n's and n squared. Just quickly explaining how this works, you'll see that as we add additional energy quanta to each level, we create differing energies for the total scalar energy. For example, at the top we have a single quantum or quanta that gives us a square number of 1. We can then add 3 more quanta to give us a square or scalar energy of 4. And again, likewise, we can add another 5 to give us a square or scalar energy of 5. All energies, as they come together, are comprised of identical energy quanta, as illustrated here. In the case of the left-hand side, you'll note that they are all odd numbers. Each level is comprised of an odd number of energy quanta, and as you add these odd numbers up in sequence, you generate the square scalar energies. These odd numbers have a term in quantum mechanics and electrodynamics. They are called bosons. They are two-dimensional energy quanta made up of positive and negative charges, which we'll discuss further on. But in all cases, because of their odd number, they have either a positive or a negative charge. They are the charge carriers in quantum mechanics, and they are the basis for quantum induction of electrical energy. When energy is released, it's released firstly as bosons, which then combine to form photons. In Tetryonics, all our numbering system follows a color code, as noted on the left-hand side, ranging from red for 1 to 2 to orange, 3 to yellow, and so on through the color code to 9 for black. At this point, if we were to do 10, we would do a different shade of black, i.e. grey, and start it again with just a differing color intensity or transparency level to these color codes to develop a color coding that's completely consistent with our decimal system of counting and how we measure things and how we do our math in quantum mechanics and electrodynamics. So the spectral color code of spectral color codes of spectral lines forms the basis of the Tetryonic color code, and in fact this is very handy when it comes to quantum chemistry. Obviously, with all scalar energies, be they 1 or x, in this case v squared energy quanta within the scalar energy, we can also calculate the square root of the energy, which in Tetryonics and the equilateral geometry turns out to be the height of the equilateral triangle, in this case indicated with a pink arrow for the net energy momenta. If this was a single momenta, this pink arrow with P on it would be the momenta for the scalar energy, or the energy momenta quantum, I should say. If there were more, they would obviously increase with odd-numbered bosons to form square-numbered scalar energies, the familiar squared energies of quantum mechanics. Again, in each case, irrespective of how many quanta there are, they will always be square numbers, and the square root will always be the net linear momentum of the energy geometry. Again, there is a direct relationship between the velocity that this momenta can create and the energy. If you measure the energy content per second, you get a measurement of mass through E equals mc squared, or more appropriately through E equals mv squared, with c squared being a specific example of that general formula, E equals mv squared. If we calculate for the mass, knowing the energy momenta in the system, we can obviously calculate for the velocity that results because of that momenta. Tetryonics now turns these mathematical equations into a visual representation of exactly what is happening at the quantum level. These are systems we'll never ever see, but we can illustrate them geometrically, and in fact the geometry of Tetryonics is the foundation for all the maths of physics. So again, just summarizing here, so far as the illustration, the linear momenta is the vector square root of the scalar energy or the mass energy in any Tetryonic geometry. 1 second, we'll explain very shortly, is just a circular measurement of the propagation of energy per unit of time. It forms a radial geometry. Obviously then the momentum itself has the units of kilograms, or energy per c squared, energy per second, by square meters, equilateral geometry per second. The Planck's constant is identical, except it is a differing measurement. It is the quantized value of energy, energy being the square number scalar. So Planck's constant is simply, you could consider it a dividing factor for this geometry per second. We can obviously express the energy as Planck's constant by nu squared, which again is just a geometric relationship between the velocity and the number of quanta required to achieve that velocity, or the energy momenta. So we have h nu squared divided by v, which is the velocity it creates, which of course is equal to also mv, which is the classical measurement for momenta. So there's a number of ways we can calculate for momentum, or specifically linear momentum in a system, with angular momentum being discrete and different. And of course we can reverse that, and we can say that the square root of the energy, or the momentum of the system squared, the square of the square root, is the energy, or it's equal to mv squared. In either way, we can show geometrically what has until now been represented mathematically. We will then go on to explain things that can't be explained through the math. The first of which is Planck's constant itself and energy. We've shown here that if we take the mass by the velocity squared, or the mass by momentum by velocity, we get a unit that is energy, kilograms square meters per second squared. We will rewrite this in the coming pages in terms of Planck's constant, where we have the mass by the equilateral geometry per second equaling the energy, or as you'll see it expressed here, mass alpha v squared or mu squared. Both symbols are more or less identical, so they're both expressed the same way here. You can reread this. Obviously it's energy, mass being kilograms, angular momentum mu being quantized angular momentum per second. So you can read this as mass velocity squared in the classical sense, or you can in fact read it as mass angular momentum, or Planck's constant, by quanta squared. Both ways of reading it are correct. It's just differing units of measurement and different times in physics as to which you choose to use. Having shown that Planck's constant is in fact a measurement of the mass, or the equilateral mass, of any energy momenta quanta, we can now apply that in a number of ways to show the quantization of energy within physics. In the case of Planck's constant, we have positive and negative charges in physics, and in both cases Planck's constant is kilograms square meters per second, or equilateral masses. The charge is simply a measurement of the dipole, whether it's a north-south or a south-north, within these equilateral geometries. Again, the electric field and the magnetic dipole can be made up of square numbers of quantas. Where a positive and a negative come together, we have a photon of energy. 2 Planck quanta makes a Planck frequency. Where you see h nu in Tetryonics, it always refers to quantum levels, as in odd numbers. Where it refers to energy itself, or scalar energies, it will be expressed as in h nu squared. By breaking or showing that Planck's constant is in fact an equilateral geometry, we can also show that the equilateral geometry itself, a square geometry per second, is just another way of measuring square meters per second. And this square meters per second is obviously angular momenta. Angular momenta in physics to date has been expressed as a vector rotation about a point in one direction or the other. In quantized energy, this is not the case. It's actually the equilateral geometry itself. It can be expressed, as you see here, as a rotation about a vector, as a classical sense. In doing this, we can in fact superimpose it on an equilateral geometry, as is done, and we can give an idea of, in electrical terms, of the flux of energy, or the flow of energy, in an ideal quantum inductive circuit. If we were to take an inductive loop of wire, a coil, energize it and short circuit the ends into a triangular shape, we would produce exactly what we see here in the form of a 0-point field. And we'll discuss this as we go further on. But while you'll see it in quantum mechanics, you won't see it in the other books of Tetryonics, because it's a learning tool, if you like. As you become more familiar with Tetryonics, you'll realize that the triangular equilateral geometries are in fact angular momentum. and it's only our macro measurements of this and our preconceptions that cause us difficulty and cause us to think that it's a rotation about a point. Taking the quantized angular momentum, or QAM, and identifying it as just alpha, we can then express it as a positive or a negative alpha per c squared, or per unit of time. In this case, the unit of time being the measurement of energy. Alpha per c squared is calculated out just as you see here. It's square meters per second being angular momentum, quantized, by the inverse of c squared, square meters per second square inverted. Calculating this out, you get units of seconds. Throughout relativity and other topics, you'll see units of time being expressed as positive and negative time. Historically, time's been viewed as a linear progression of entropy, or likewise, in many different fields of physics. In Tetryonics, we reveal time to be the measurement of quantized, or the flux of quantized angular momentum per unit of measurement. In this case, we use c squared being the measurement of the motion of energy, and as we're measuring the geometries, we're determining any changes in that geometry. Therefore, it's generating a unit of time for us. So where you see positive and negative time in other formulations, you can quickly relate it back to being positive or negative charge in Tetryonics. Likewise, quantized charge is normally expressed with a small q. Normally it's a number, but it's written as a small q for quantized charge. The net charge is a capital Q. In both cases, they're the result of positive charges and negative charges not quite balancing themselves out within the square equilateral geometries of energy. This shows us that in Tetryonics we can show the full formulation for Planck's constant as kilograms square meters per second as being the equilateral, as an equilateral measure of energy, or mass in this case, because we're using kilograms. So kilograms mass, square meters is the equilateral geometry, per second is just the unit that we're measuring it in, how many, what the change is in that unit of time. Could be a different unit of time, would only change the units. Of course, you can split Planck's constant up in a number of different ways. You can make it a measurement of energy by time, scalar, by the time that you're measuring it in, and you can also measure it as a take it as a measurement of the momentum that's acting through a linear distance in the system being measured, or the force, if you like. Tetryonics can obviously show you all the geometric relationships that relate to the different formulations, and in turn giving you the geometry of Planck's constant itself, mass and energy. Again, noting that transverse quanta create the quantum levels. The bosons are transverse bosons, and they're always odd number of quanta, and the scalar are always squared numbers. That's the scalar energy. And of course, if you measure energy per unit of time, you get a measurement of mass. Again, we hone in on Planck's constant, which is normally called the quantum of action. In this case, we can reveal the physical geometry of Planck's constant, i.e. equilateral energy or equilateral mass. It's got a specific geometry, a specific area of square meters that the geometry covers per unit of time. This, as we've discussed, can be drawn as a electrical flux of energy, which will then show us relationships as far as inertial mass, etc., how that can be explained in terms of electromagnetics and electrical energy. But in all cases, we can show Planck's constant h to be nothing more than mass by quantized angular momentum. And in this case, obviously, the alpha, or the quantized angular momentum, is simply the equilateral geometry of the quanta in any scalar energy. It's the quantization that brings about quantum mechanics. What was failed to be recognized was that it was an equilateral geometry. Obviously, if you're referring to positive and negative charges or positive and negative masses, the only real difference is in their geometry. In Tetryonics, strictly, it's the only difference is between their dipole arrangements of the north and south poles, and it is that arrangement that determines whether it's a positive or a negative charge. In electrical theory, we can draw this as a flux of energy flowing between north and south poles externally back into a south to north flow of energy within the dipole. And this rotational flux is just a handy short circuit again. Tetryonics, we can also express force, which is the result of momentum over time, which is just again the square root of the scalar energy. So we have energy momenta, which again is Planck's constant, showing us what force is and the direction that it acts. Obviously, there is a subtle difference between energy momenta, which is a linear force, to that of Planck's constant, which is a mass quantized angular momentum, or mass alpha force. The energy momentum is the square root, the momenta is the linear momentum, whereas in Planck's constant it is the quantized angular momentum, or it's a scalar measurement of the equilateral geometry. A measurement of the equilateral geometry per second, or energy per second, gives us mass, whereas a measurement of the geometry, the quantized angular momentum per second, gives us charge. So again, just to make sure that we're clear on that, energy momenta is a linear force measurement. Planck's constant, or mass alpha, is a charged mass measurement, where the energy per second is measured, forming mass, and where the quantized angular momentum, or the geometry of alpha, produces the charge. These charged geometries can obviously come together in a number of ways, but they all form equilateral geometries of square numbers. It's the equilateral geometry that forces an imbalance to be created when you add energy momentum to charged geometries. In the case of negatives, you'll find that even though they have the same, in this case the same square number of quanta, there is always an imbalance where the negative are on the outside. And likewise with the positive will always form in excess on the outside of the geometries. These geometries, positive and negative, obviously have square root energy momenta, as drawn on the left hand side here. Classical analysis of energy in Leibniz and in Newton's case, Leibniz measured the energy, or the scalar energies of the system, E equals mv squared, whereas most of Newton's formulations concentrated on changes in momentum, linear momentum particularly, in which case he was looking at the square root, mv. Scalar measurements shown clearly with the Tetryonic geometry in this case. Planck, on the other hand, showed that it was a quantized system that was of a quantized measurement of energy that was producing the light and the black body radiation he was researching. So again, Tetryonics shows that instead of h to be mass alpha nu squared, or mass velocity squared, which is the same thing as what Leibniz was measuring. These are all different measurements of the same properties, or similar properties, of energy. We're just measuring force versus scalar energy versus quantized energy, in this case Planck quanta per second, to give us joules. Tetryonics can obviously take these differing measurements now that we have a common geometry and re-express them in a form that can be used over and over, an expression for energy. In this case we use mass alpha nu squared, or mass alpha nu squared as reading across the top, which is just another expression for Planck's constant nu squared, the right hand illustration where it's quantized. Accordingly, we can measure it as mass velocity squared. They have the same relationships, velocity to quanta to velocity squared. It follows this, it's derived from the equilateral geometry in both cases. So we can write it this way as mass alpha nu squared, and we can also read it as mass velocity, providing we understand what's being written in this case. There may be other formulations by mathematicians in years to come. I found this to be most efficacious so far as explaining things, particularly where you measure these units per second or per c squared, and you measure the angular momentum of the EM field, or the number of quanta that's in the EM field. By measuring the angular momentum of the EM field, you're also creating a measurement of charge. So in this case the alpha will give us the charge of the electromagnetic field that the energy is creating. So again, you can see the charge, you can see the equilateral geometry, you can see a measurement of mass, and you can see this proportional, that whether you measure it in a quantized fashion of quanta squared or velocity squared makes no difference. They all follow the equilateral geometry of the charge of the EM field, which again is per c squared. That is energy. It's specifically a charged mass or a charged energy, depending on your units. Again, here you have an illustration showing the idealized electric flux or electrical flux of energy. This does not actually exist. It is a property. The quantized angular momentum, again, to harp on it, is a measurement of the equilateral geometries. This rotation is purely there as a guide for other properties. The c squared around the outside differs from the inverse c squared of the magnetic field, of the EM field I should say. The c squared in the circular geometry is simply the circular time measurement of energy of light propagating at the speed of light. So energy in 1 second will go c squared in two directions, forming c squared, a circular geometry. A lot more is covered on this in greater detail in quantum mechanics and in ebook 4, cosmology specifically, where we go into spatial coordinate systems, c squared, c to the third, and c to the fourth, specifically as the spatial geometries. Obviously, as we have a triangle without a circle around it is purely energy, and the size of that triangle is determined by the number of quanta in it. However, a measurement of energy in a unit of time, the geometry of the energy is dictated by the unit of time that you're using to measure it. So in this case it's 1 second, or c squared, so we're measuring all the energy that's found within that 1 second unit of time. It may turn out that 1 second wasn't sufficient to cover all the energy that the system had in that region. Again, you have to be careful whether you're making your measurements per unit of time or per the energy content. One is mass, one is energy, and there are distinctions between the two, covered in greater detail in cosmology particularly. We can now, using Tetryonic geometry, reveal what a 0 point field is, or what 0 point energy is. As illustrated in the middle of this picture, 0 point energy is charge. Specifically, it is the charged Planck quanta, one side of the quantum coin or the other, that you're measuring. It has an equilateral geometry, and it is one quantum of work Planck's constant. You will note that where the squared nu normally is, or v squared, we now have a half f. This indicates that in the case of quantum oscillators and the such harmonic circuits, to create a frequency f, you need two charge quanta, a positive and a negative, to create a frequency, or a photon of light, photon of energy. So you'll see in a lot of different formulations mathematically, the 0-point energy is expressed as E equals h, or a half hf. This is what it is. It is Planck's constant by half the frequency, or just plainly Planck nu. Again, you can express it as Planck nu, as you see on the left hand side, because it is A, charged, and B, it is a quanta of 1 being an odd number. So legitimately it is E equals h nu, or E equals a half hf. You could also express it as a half h nu squared, just as legitimately, if you're referring to the scalar energy. If you then said half h nu squared divided by c squared, you begin to see the scalar Lorentz corrections, and you also have a measure of mass per unit of time, or energy per unit of time, which is of course mass. As we've discussed, the only difference between positive and negative charge geometries is the arrangement of the magnetic poles within their dipole. A positive charge having a north-south, a negative having a south-north. These can be drawn a number of ways, as illustrated here, with the magnetic and the electric fields. And they can also be represented in a stylized format for chem fields, which we'll cover in due course. As we've seen with the charges being determined by the magnetic pole arrangement of the dipole, and as we've expressed already with quantized angular momentum being a misrepresentation of equilateral geometries, we can also draw an electrical equivalent of the 0-point field by having a helical inductor charged up and the ends of it short-circuited. In the case of 0-point fields, or 0-point energy, the energy within the field that creates the field, these quantum inductive circuits are ideal. They don't lose energy at all. In real life, obviously, there'll be losses due to resistance and the like. At the quantum level, there is no loss of energy, predominantly because there is no flow of energy. It is the result. The electromagnetic field is the result of the geometry of energy itself, as we've discussed. It can, however, be modelled as an ideal inductive loop where the energy flows in one direction or the other, and this aids us so far as determining things like inertial mass and explaining it. Of note is the fact that in quantum inductors, or 0-point fields, the energy doesn't oscillate. It always flows unidirectionally in one direction or the other. And again, a negative charge viewed from the other side will be a positive charge. You can cut the illustrations out, hold them up, and turn them around and look at them from the other side. You'll see that a negative is in fact a positive on the other side, and a positive is a negative on the other side. This is mathematically expressed as a Lorentz transformation of the EM field. Mathematically quite complex, physically using Tetryonics quite simple. Turn the page over. The magnetic dipole that this triangular or equilateral energy quanta form or contain is enhanced as you add more quanta, obviously, but the magnetic dipole itself, apart from determining the charge of the field, also is what is termed in our physics as the weak force. It is the coupling of magnetic fields or inductive dipoles that is the weak force in all quantum mechanics Again, quantum mechanics goes into this in much greater detail, particularly the lecture on equilateral energy. The fields themselves are just electromagnetic fields. As we've discussed, this can be mathematically represented as shown here. We can show them as electric permittivity by magnetic permeability, which gives us a number of 1 over c squared. Again, we can show this 1 over c squared geometrically as the equilateral triangle with a E field, diamond shaped, and an M field, or a dipolar M fields. Noting, of course, that there are 2 pi M fields and there are 2 pi E fields, in total making a 1 pi charge field. The energy within this field is obviously electric or magnetic, depending on how you measure it and what you measure it with. Tetryonics, as we've discussed, you can take the equilateral energy and measure it per unit of time and come up with mass. Mathematically, all we're doing here is we're saying energy, again, mass alpha nu squared, which is energy of the EM field per c squared, and the number of quanta in that field. So n pi squared if you want, because there'll always be a square number. In this case we have 1 pi. We have an electromagnetic field of a certain energy, which gives us the mass. It's as simple as that. Mass is just in most cases it's a charged mass. All matter is comprised of charged masses, equilateral in fact, and this equilateral energy masses creates the geometry of all matter. Hence why Tetryonics is normally referred to in most cases as the charged geometry of mass, energy, matter. In all cases it's a concise description of what Tetryonics is about. Maxwell was the first to calculate this 1 over c squared, and he quickly realized that if you take the square root, i.e. the momentum of this energy field of c squared, 1 over c squared, you come out with the velocity of light in a vacuum. Obviously then this can be re-expressed in terms of the electric fields and the magnetic fields to give us constants for both, either in units of farads per meter and henrys per meter, or their physical equivalents. And in the case of light, where we join a positive and a negative charge together to form a photon or a frequency of energy, again noting 2 h nu equals 1 hf, we can get a quick visual image of what a photon of electromagnetic energy looks like. We have the magnetic fields, the photons, the Evans photomagnetons of photons, and we have the electric fields, positive and negative, although in this case they're generalized as electric fields. Again, we have opposing energy momenta, and normally this would create an electrostatic field, or in the case of light, they radiate out from their source in both directions at the same time. It forms a natural expression of the Poynting vectors, where the Poynting vector itself is the result of the electric times a cross product of the electric times the magnetic fields. Looking closely at the EM field permittivity of any EM field, again, as you see, it's measured in a number of different units, but it is always a diamond shape, as seen here. These shapes have been highlighted in the case of positive and negative charges. Again, there is no real physical positive or negative charge per se on these. These positive and negative charges are determined by the magnetic poles of the dipoles, whether they're a south-north in the case of negative or a north-south in the case of a positive. Gauss obviously formulated a lot of rules and laws for charge as it exists. These form the basis of Coulomb's laws of charge. In all cases you'll see terms like 4 pi popping up inverse of r squared and the like with respect to charge and electric force. In all the cases, it was assumed that 4 pi referred to the spherical geometries. In fact, Tetryonics shows that 4 pi relates to, in the case of matter, relates to tetryonic or tetrahedral geometries. The measurement of the of two fields, where you have two electric fields, two charged fields I should say, coming together of similar charges, i.e. two positives or two negatives in this case, they interact via their magnetic dipoles or the weak force, and when they do so, because they have similar charges, the orientation of their magnetic dipoles results in a pairing of a north-south pair, which you can consider to be neutralized from a physical measurement using magnets to detect the magnetic field of such an arrangement of similar charged fields or coupled fields. You will not be able to detect the magnetic dipoles that are present, because obviously if you move in a south pole, the south pole will repel it and the north pole will be attracted to it, so there'll be no net force no matter how you choose to measure it. You will, however, be able to measure the electric field because it is a purely negative, unless you Lorentz transform, look at it from the other side. It's a negative field. Likewise, if you have two positive charges coming together, their momenta will cancel out. The particle will be stationary, and the magnetic moment or the magnetic dipoles of the fields will be undetectable. You can obviously not only model these with equilateral geometries, but you can in fact model them with the electrical fluxes of energy as well within the quantum loop geometries. We can represent these fields as shown in the middle of the picture with two charged geometries back to back, again with the magnetic dipoles being neutralized, and they're static because the energy momenta of both fields cancels. You'll note down the bottom that all energy fields, or all squared energy fields, are comprised of differing momenta. Again, as we've mentioned with charge, there will be positive and negative charges, the net charge being important in determining the total charge of the electrostatic field. And in the case of negative charge electrostatic fields, obviously there are more negative charges than there are positive. In the case of positive electrostatic fields, there are more positive charge energy momenta than there are negatives. And it's this imbalance between positive and negatives within the EM fields themselves that gives us the basis for the law of interaction, as it's been formally termed historically. Tetryonics changes this into the law of interaction because of the opposing energy momenta. We can draw this in a stylized form again as a spherical charge, which it is not, with radiating fields. In the case of positive charges, it's the positive that radiates out, is divergent, with a convergent negative energy momenta. And in the case of negatives, it is the negative that is divergent, being the larger number, and the positive that is convergent. And it's this difference, the making up of EM fields of force out of convergent and divergent energy momenta, that leads to the law of attraction being retermed in Tetryonics to the law of interaction. Obviously the same thing can be done again for an EM field, where we just again ignore the E field components and highlight the M fields that make up the dipole of each field. Obviously we can express because it's a squared energy geometry and the electric is proportional to the magnetic, we can express the magnetic as a measure of the total energy divided by the electric. They're measured in Faradays or other units, as expressed here in Henry, and other units. Again, we can concentrate on, we can use the stylized electric schema for angular momentum to give us the electric flux, the magnetic vector even between the magnetic poles. We can see that externally it's always north to south, internally it's always south to north within the 0 point field. Most importantly, as you'll note in the center diagram, is that there are two magnetic poles forming a dipole for every energy quanta and every energy field. There are no magnetic monopoles under any conditions. You might measure a magnetic pole in one form or the other, or from one direction or the other of a field, but every field and every quanta of energy has a magnetic dipole. Again, just like electrostatic fields, we can have opposite charged fields coming together where the opposite charges, electric charges, cancel out, giving us a stronger, more measurable magnetic dipole, where instead of north-south we have north-north being formed by the two charged fields coupling by the weak force. This arrangement can be mimicked in the macroscopic world with a electromagnetic coil or a bar magnet. Either way, they are all forms, and in both cases what it shows via Tetryonic geometry of equilateral energies is that wherever you have a magnetic field, you also have an electric field, and likewise wherever you have an electric field, you have a magnetic field, just as expressed in Faraday's laws. And in Ampere's law, where a current moves through a conductor, we can in fact use the equilateral geometries to model not only the point charges, the electrons, but also the chem fields, the kinetic EM field that's created by the particle when it's in motion. Again, these chem fields are equilateral because they're made up of equilateral energy quanta, and they have two parts. They have an electric part. Because it's a two-dimensional field, this is normally termed the kinetic energy, a half mv squared. But where the electric field exists, you also have a magnetic field, and in this case the magnetic dipole is equal to the kinetic energy, a half mv squared. The kinetic energy and the magnetic dipole is the same as the electric and the magnetic dipole. They all have equilateral geometries, squared energies, and they can all be modeled using Tetryonic geometries. In this case, you'll see down on the bottom half of the page where we've modeled charged particles, in this case electrons, -1 elemental charge, in motion. Around the charged particle we have the chem field, the kinetic EM field, kinetic energy and magnetic moment that's created with the motion of these charged particles in a conductor. As they're accelerated, obviously, at whatever velocity they're accelerated at, there's the square energy quanta to move them at that velocity. But their chem fields always mirror the charge of the particle that's being accelerated. In this case, it's a negative particle, so we have a south-north dipole arrangement. If it was to be a positive charge to the right here, it would be a north-south dipole arrangement in the same direction with a positive charge instead of a negative, although the charge itself is not detectable. In this case, we have two electrons moving in the same direction. They both create negative chem fields, so we have a situation where the north and south poles of these magnetic moments of the electrons in motion attract each other. So two charged particles moving in the same direction are attractive. Two charged particles moving in the opposite direction generate a repulsive force due to their magnetic moments between the particles. And that's a clear illustration of Ampere's laws, where charges moving in a conductor generate different forces between those charges in the conductors. They're historically drawn as illustrated at the bottom. However, they can now be quickly drawn and concisely drawn for all their energy properties and geometry using Tetryonic geometries. As we mentioned, where you couple two fields together of the same size, the energy momenta, as illustrated in the middle of the picture, cancel each other out. So long as these fields are of equal size or equal strength, same energy quanta, they will cancel each other out and create static fields. Now, depending on whether they're similar or opposite charges, you will create either electrostatic fields, where the electric field is enhanced, or magnetostatic fields, where the magnetic dipoles are enhanced. But in both cases, again, where a magnetic field exists, there is always an electric field, and where an electric field exists, there is always a magnetic. It is just the geometry of these fields that means when they come together, they will be more or less neutralized or undetectable to large-scale measurements. The Tetryonic geometry of energy and EM fields in particular shows us that they still exist. In the case of energy fields, where these particles, electrostatic ones, where they form with similar charges back to back, they obviously have energy momenta, square numbers, and they have divergent and convergent energy momenta or charges for each charged field. In the case of negatives, there are more negative energy momenta, so it's the divergent part of the field, and the convergent part of the negative field is positive charges. And likewise with positive charges, the divergent energy momenta are positive and the convergent are negative. Obviously these fields can come together in various ways. In the case of the middle one, we wouldn't have an electrostatic field, we'd have a magnetostatic field, because the positive and negative charges would neutralize but enhance the magnetic dipole of the two fields. However, of note is when we model our positive and negative charges that are free to move through space using their point charge geometries and their kinetic fields, we note that where a positive charge moves into the region of force of a negative electrostatic field, the positive charge is actually accelerated by the convergent positive energy momenta towards the particle. If it was a negative particle, it would be repelled away or slowed down as it tried to approach the negative charge by the divergent negative charges, and likewise with positive charges in a positive field. It's these divergent and convergent energy momenta within the square energy fields, two-dimensional energy fields of electrostatic fields, that creates the force of interaction, or what used to be known as the force of attraction. It's retermed the force of interaction because obviously, dependent on whether it's a positive or negative charge, it may be attracted or repelled within that field. There are no virtual particles pushing against the particle as it approaches the other one, or anything of that sort. There is a physical geometry, equilateral geometry, to the energy momenta that the first particle creates, and that acts on the second particle as it approaches it. Again, as an electrical force, it's 1 over r squared. Quickly reviewing the law of attraction in terms of energy momenta, we can see that with the magnetostatic fields at the top and the electrostatics at the bottom, we can see how the energy momenta or charge fields can join together with differing energy momenta. I've highlighted in this case highlighted the stronger field that results, the magnetic versus the electric in this case. But in both cases you can see that there still remains energy momenta of both within the field. You can use the equilateral geometry of the electric and magnetic fields to show the law of attraction, as it used to be called, or the law of interaction. And what we can also show, we can model this again, of course, with electric fluxes. They will show exactly the same thing as what's shown with the equilateral geometry, whether they attract or repel depending on their arrangements. But what we also show through the geometry is that electric fields have a differing equilateral geometry to that of magnetic. The electric is a diamond shape, back-to-back, 2-pi geometry. The magnetic is a separated 2-pole or dipole magnetic fields, two distinct, not combined. They're not a diamond shape. It's this distinction between diamond shapes and two single equilateral geometries that creates a difference in the strength of electric and magnetic fields. In the case of the electric, they taper off as 1 over r squared. They're an inverse squared law. In the case of magnetic dipoles, they taper off as an inverse to the cube of the distance. If you were to measure it strictly as a dipole, it will, in the same distance from the source as the electric field, it is far weaker than the electric field. Electric fields act over a much greater distance than the magnetic dipole does. Magnetic poles are a different case to the magnetic dipole. The magnetic pole is 1 over r squared. The dipole is 1 over r cubed. Just an important point to note. As we've discussed, it's now called the law of interaction because we have convergent energy momenta arrangements as well as divergent energy momenta arrangements within any charged force field. Where these fields overlap, obviously the differing energy momenta of the superposition fields creates differing forces between these fields. And if we look closely at the three possible combinations, i.e. charges between force fields between two similar charged objects, positive, two positives or two negatives, versus the force between differing charges, we see that in the case of similar charges, the energy momenta act against each other. They both try to repel each other with a superposition. Same with positive charges. But where we have opposite charges, where they overlap, the positive is reinforced and pulled towards the negative, and the negative likewise is pulled towards the positive. So we have an attraction versus a repulsion. And again, that reinforces the change of name to law of interaction for electric fields. This is the same law that's used for Coulomb's force and similar ones. It's not the same forces that generate gravity. Again, with scalar energy, as we've touched on before, all odd-numbered geometries are bosons. 1, 3, 5, 7, 9, 11, 13, 15 onwards. They're all bosons. They're all odd-numbered geometries, and they're normally described, the energy content is E equals h nu in Tetryonics. They combine sequentially. 1 plus 3 gives 4, 4 plus 5 gives 9, 9 plus 7 gives 16, 16 plus 9 gives 25, and so on, to create squared numbered scalar energies. So electromagnetic charge bosons create square scalar energies, and if you measure that per unit of time, you get square energy masses or mass energies. So again, to highlight the fact that where you see odd number of pi geometries, you know it's a boson. Normally they're indicated in Tetryonics with an orange or a golden shape to highlight the fact that they are a charged geometry. Again, the net charges, or the final charge of each energy geometry, is the result of the positive and negative charges within that geometry. There are a number of ways of combining W bosons to create energy geometries, as you'll see. Interestingly enough, you can measure transversely, and you'll see in a lot of textbooks a thing called transverse masses or transverse energy. That's just the measure of the bosons, the boson energy itself. You can also measure it longitudinally with respect to the momenta, the square root of the energy geometry, or the direction of the chem field for particles in motion. In which case you'll see that they form positive negative pairings in that direction. Bit hard to see in here, but if you were to join, for example, the two bosons here together, you'd have a positive and negative, and then you would have a positive and a negative when these two join together, and a positive and a negative. So you could form these 4 W bosons to form 3 photons in the longitudinal sense. They are still W bosons transversely, or transverse masses, W bosons, but longitudinal masses are in fact the photons. And if you look at the distribution of photons, ignoring the half photons at the bottom for charge geometries, but if you look at all the geometries, be it quanta or be it photons longitudinally, you'll find that they follow a normal distribution. If we quickly show it here, we've got 1 quanta, 2 quanta, 3 quanta, 4, right through to 8 quanta in the middle. Then they count backwards: 7, 6, 5, 4, 3, 2, 1. So we go from 1 to 7, or 1 to 8, sorry, and from 8 down to 1. This is normally plotted in mathematics as a bell curve, or a normal distribution. In quantum mechanics, again, Tetryonics shows us that the distribution, or the normal distribution, bell curves, that forms the basis of statistical probabilities in quantum mechanics, is in fact an equilateral geometry. And the pi here is not a measurement of spherical geometries, it's pi radians. Obviously, when we add energies to an electron to put it into motion, we're adding energy to the chem field, not to the matter of the electron itself. That is to say, the mass of the electron itself, its matter, is Lorentz invariant. It does not change as you increase its velocity, as hypothesized in special relativity. It does not distort as in special relativity. It is not a spherical geometry as implied in special relativity. The magnetic moment that results, well, firstly, a electrostatic electron, one that is not moving, has 12 negative charge geometries, and obviously they will affect a positive charge in the normal ways. They will attract it and repel the negatives as they approach closer to the charge geometries themselves, and they're an angular geometry. This is a side elevation on this page of electrons. The next page we'll see a polar elevation. They are angular. They're very much like the stealth fighters that you see in war books and movies at the moment. They have an angular geometry. They're not flat. So they have various degrees of interaction within themselves. But all their energy of motion is contained in their chem field. You'll see the arrow for the linear momentum. There is a chem field, an equilateral chem field, where all the energy of motion is contained. And it's this equilateral chem field, or square energy numbers, it's the linear momentum that this field creates that moves the particle forward. The particle itself does not have any additional mass energy. All the mass energy of motion is stored in the chem field. And we highlight this again with different colours on the electrons and their geometries, just to show that there is increasing energy within the chem field of that electron. But in all cases you'll see that they're all 12N for their mass matter geometries. That is invariant to velocity. What changes is the kinetic energies of the chem fields in all cases. We can stylize this with circular geometries and whatnot to give us pretty pictures. But again, rest matter is rest matter. Adding all the energy of motion goes into the chem fields. You can add the mass energy of matter to the mass energy of the chem fields to give us the changing mass energies of particles in motion. But the basis that special relativity was formed on with Einstein being the velocity distortion of spherical charges to create magnetic moments, is completely erroneous and incorrect. Particles themselves are not spherical point charges, nor are they distorted in any shape by their velocity, nor do they have any energy added to their matter geometries from their velocity. All the additional mass energy goes into the chem fields, as illustrated on this page. You can see we start off with a N1 electron. A bit of a mix-up on this page, but these two numbers are reversed. Again, the matter in all the cases for these electrons remains the same. The mass matter is 12N, or 1.2 by 10 to the 20 quanta, and it never changes, no matter how much you accelerate it. Obviously, as we do accelerate the electrons from a velocity of 1 upwards, doesn't matter what it is, the energy that's required to accelerate it is in the chem field, and it's the square of the velocity. It's the linear momentum, or the square root of this energy, that creates the motion of the particle. There is no additional mass added to these particles. All the mass energy is stored in the chem fields, and you see this in this illustration. You can see as we add energy and increase the velocity up to 8, the energy content is increasing, and the magnetic moment of the electron is increasing and growing stronger, just as it does in reality in all physical measurements. But it does so using a completely different geometry and a completely different explanation to that of special relativity. Tetryonics not only undermines special relativity, but it completely undermines general relativity and re-explains it in terms of equilateral geometries. These are major foundational changes to relativity theory, and the reason why they stand the test of time is that they've been applied to not only relativity theory itself, but also to fields such as gravity, chemistry, quantum mechanics, and electrodynamics, as we're doing now. We can obviously create a stylized version of particles in motion, listing the matter as a capital M, as it always is in Tetryonics. Mass is always written with a small m, and we draw the kinetic energy fields of kinetic energy plus the magnetic moment, the chem field, as an equilateral field in the direction of motion of the particle. Obviously it's the linear momentum of the chem field, the square root of the energy, that creates the direction, or the motion of direction, for the particle in this case. And we rewrite kinetic energy as matter velocity squared, mv squared, not mass velocity squared. Still refers to the same thing. It's the mass content of the matter in motion, but you'll see that when it comes to gravitation, it is much better to write capital M for matter, small m for mass, so as to clearly distinguish between the two. Special relativity, or relativity in general, lumps mass and matter and energy together as just energy in the stress energy tensor. Tetryonics does not. It has specific geometries for both. Just briefly recapping on what we've just done on electromagnetic fields themselves. Obviously they are physical fields of force. There are positive and negative charge fields made up of positive and negative charge quanta. They have distinct dipole arrangements of their magnetic fields, and there are always a dipole or two magnetic poles in each energy field. Magnetic monopoles do not exist. And likewise, it's the arrangement of the magnetic poles in the energy geometry that gives us positive or negative charges. These charges can come together to form photons of energy with discrete magnetic moments, and likewise they can create charge geometries of chem fields where we have a discrete magnetic moment. There is a difference between photon geometries and chem field geometries, namely one is 1 pi, the other one is 2 pi. Biradiant energy form, unidirectional motion from the energy momenta in that field. Obviously, the magnetic vector is always 90 degrees to the electric vector, and the electric vector is always in the direction of propagation for longitudinal fields, and orthogonal to it, or transverse to it more correctly, in the case of transverse fields. They're covered in more detail in other lectures. Obviously, all electromagnetic fields can be square energy quanta, or have any square energy quanta that is proportional to the velocity of their motion. And again, measurements of energy per unit of time gives us measurements of mass. These fields, positive and negative charge fields, can come together to form electrostatic or magnetostatic fields. All energy from Planck quanta through to heat, light, and electric forces, and even in a slightly different formation, gravitational forces, are electromagnetic in at their base level. The energy quanta and the electromagnetic fields are equilateral. All mass energy and matter itself is formed on equilateral energy geometries, and it's mistaking square numbers, or not identifying square numbers for equilateral geometries, that's created a roadblock in our understanding of physics. Maxwell, in quantum electrodynamics, or electromagnetics as it was at his time, unified the discrete formulations for electric fields and magnetic fields into a set of laws which now have become known as Maxwell's equations. These equations are written in a number of different formats using different mathematical representations and formulations. But in summary, they are obviously Gauss's law of electric flux, which is describing the energy momenta and the divergent and convergent forces of these electric fields. Gauss's law of zero net magnetism, which is simply stating that there are no magnetic monopoles, that you always have a magnetic dipole with an electric field. Faraday's law of induction, that wherever you have magnetic fields, you also have electric fields, and equivalently, wherever there are electric fields, you also have magnetic fields. Even if you can't physically detect them, they are present. All energy is comprised of electromagnetic fields. And Ampere's circuital law, that in a conductor with charged particles in motion, a magnetic field will be created around that conductor that will cause interactions in direct proportion to the velocity of the charged particles in motion. Again, these are reformulated various ways, but Tetryonics reformulates them in terms of equilateral energies, or EM fields. Obviously, in the case of charge, we have equilateral energy fields with differing divergent and convergent energy momenta within each. The arrangement of the magnetic dipoles gives us positive or negative charges, and likewise the differing positive and negative charges within any energy geometry as a result of their quanta gives us a positive or negative charge geometry. Traditionally, Gauss formulated all this from spherical or even square integrals of spherical geometries. In reality, they are equilateral geometries. All charge is equilateral. The illustrations you see of spherical point charges or spherical surfaces with a square integral section measuring the charge within that area should be redrawn to be equilaterals. You can still measure them with square integrals, but the exact number will be made up, the exact area will be made up, integral area will be made up of equilateral geometries. And as we've said, you have electric constant and magnetic constant for the electric and magnetic permeability and permittivity of the EM field, or the charged region, and it is the orientation of the magnetic poles within the magnetic dipole of the field that determines whether it is a positive or negative electric charge within that field. Again, capital Q for net charges is determined by summing up all the positive and negative charge quanta within the integral area. Ampere's law simply shows that any charged particle in a conductor that's subject to an electromotive force will create magnetic forces around that conductor. These forces are obviously the result of the energy in the chem field of the particle in motion. As discussed in Tetryonics, whatever the charge is of the point particle in motion, the chem field will have a similar charge orientation of its dipole. In this case, a negative charge moving down off the page will have a south-north chem field. A positive charge moving up the page will have a north-south chem field or dipole as a result of its positive charge. Tetryonics can use the equilateral geometries to quickly determine the magnetic fields present and illustrate them, as opposed to using left and right hand rules for conventional or electron flows within circuits. We can use the one geometry and our knowledge of the magnetic dipole arrangement of positive and negative charges gives us quick, easy answers for such circuital analysis of charges in motion. In this case, we've highlighted negative charges on the left and positive charges on the right, drawn their chem fields in the direction of their motion, and we can see what the magnetic dipoles around the conductor will be. We can also see to either side of these charges in motion what creates the motion, namely the electromotive force, which is the result of separated charges. When you separate the charges in any region of space, they'll follow Tetryonics' second law and they will seek equilibrium. They will remain in this fashion in the case of a battery as they're stored in plates, but where a conductor is placed between the positive and negatives, the energy momenta will flow almost instantaneously between the charged, or the regions of charge, and any charged particle in the circuit along that along the energized circuit where the energy is flowed will obviously be accelerated. You can quickly see this by the charged geometries using Tetryonics. You can see that in the case of the left-hand drawing, negative charges will be pushed upwards on the page, driving it around the circuit in a clockwise direction, whereas the same voltage arrangement, or EMF, with positive charges will push the positive charge in a differing direction. Well, in this case, because we've reversed the illustration, it still flows clockwise, but if they were both to the right, the positive will actually be flowing in the opposite direction. You see from the arrows that if this was drawn with the positive charge to the right of the EMF, in fact the positive charged EMF, or the momenta, would drive it in an anti-clockwise direction. And by illustrating it this way, we can show the various numbers of or permutations of circuit arrangements that result, and that's what creates the numerous number of left and right hand rules in electrical engineering. We can resolve all of these laws using Tetryonic geometry. We draw the circuit with the charges, we can quickly determine which way this charge will flow and what magnetic dipole will be created around the conductor that it's flowing in. Faraday's law of induction, again, states that where there is a magnetic field, there is an electric field, and where there is an electric, there is a magnetic. This case we've illustrated with a bar magnet. Historically, everyone associates the bar magnet with a magnetic field. Some people will know that it contains a block wall in the center of the field of the bar magnet, where the north field becomes a south magnetic field, and vice versa. And it's always been speculated what's going on. Obviously, you can cut a bar magnet up time and time again, and each time you cut it up, you will obtain a north and a south field. You can prove this with equilateral geometries. Every time you cut this geometry up into smaller fields, you will always have a north and a south dipole arrangements of the quantized energy. Equally, where the block wall is, it's now shown using Tetryonic geometry that there is an electric field. Of note is the fact that it is a two-dimensional field. This is just one slice of that field. In reality, there would be many, many slices forming a three-dimensional field around the bar magnet. Even though it is undetectable because it is a two-dimensional field and the north and south charges, electric fields, cancel each other out, or neutralize, probably a better word. They don't physically cancel. They're still present, and it still contains the divergent and convergent energy momenta in these electric fields. So if you were to form a loop or a conductor of wire and move it across the magnet, you will move from a magnetic field into a region of electric energy momenta that will, just like a battery or an EMF, will act exactly the same. The energy momenta will create a force on charged particles within that conductor, the electrons, and move them. In this case, we have a positive negative field, and as this conductor is moved across the magnet, it will come into the EMF field of the bar magnet itself, and this EMF field with its energy momenta will drive the electrons downwards on the page. This can also be explained as a movement of positive ions or positive particles in the opposite direction, conventional versus electron flow. Both of these flows are explained with Tetryonics, can be modeled with Tetryonics, and this full explanation is in stark contrast with the explanation given by Albert Einstein in his special theory of relativity. As we've noted, if we separate charges, we can do so into positive and negative charged fields, and when we do so, we create the potential for an electromotive force. If we connect these charged fields with a conductor, the charges will seek to equalize. They will flow through the conductor and seek to equalize their energies. In doing so, they will motivate positive and negative charges in that conductor to move in one direction or the other, either in conventional flow or electron flow. Reality is they always move in electron flow because it's the electrons that move, not the protons. With separated positive and negative charges, they obviously can contain their equilateral geometries. It's the quantized angular momentum, or the equilateral geometry, that determines the charge, and the energy quanta within each equilateral geometry is always a square number. This square number of quanta will obviously create a linear momentum or a linear force. In this case, we term it the electromotive force, and the force that it can create is proportional to the square root of the energy quanta within that field. As you add more quanta to the charge geometry, you have the ability to create a larger electromotive force when the circuit is completed. A measurement of how many quanta within a charged geometry is simply the measurement of voltage or the energy pressure that's created per charge. So voltage, again, you can read it off as the square root of the energy, but it is the energy momenta within that charge geometry that has the potential to do work. When you connect it, the energy will flow one direction or the other. And looking at the divergent and convergent directions of the positive and negative charges gives you the direction that negative charges, for example electrons in conductors, will be forced to move. So as the circuit is placed between the positive and negative voltages, the voltage then, due to the number of energy quanta per voltage geometry, has the potential to drive negative charges from the negative into the positive voltage. And that's how batteries work, that's how generators work, and that's what voltage really is. It's just a measure of how many quanta per charge geometry, or separated charge geometry. Of course, we can measure these not as energy quanta, we can measure it as total energy, or as joules, which is just kilograms square meters per second energy, kilograms square meters per second squared. Again, that's just Planck, the number of Planck quanta per second. It's a measure of energy. As noted here, it's Planck's constant by the frequency, or the measure per second. It can be a measure of mass by the velocity squared, or it can be a measure of the potential momentum that these energy momenta create by the velocity that they will drive particles through the circuit with. Again, joule is a measure of energy or force. Linear momenta produces a force or a potential force per charge. These can all be related back as via Newton's formulation for force, or via Einstein's formulation for mass for the same geometries. You will note that in all cases in electricity, they are all masses, mass energies. There is no matter involved. The mass energies of the electrical energy will induce motion in matter, but they are all mass energies. Obviously, again, Tetryonics can redefine units such as coulombs and amperes in terms of mass and or energy geometries and their equilateral quanta. And we can see that coulombs can be directly related as the inverse of amperes. Coulombs are a measurement of seconds per kilogram, strange unit, but more rationally, amperes are a measurement of charged masses per second going past a point. As you can see here, mass per second is a measure of amperes. So we're measuring the physical amount of electrons, in this case, moving past a point of measurement per second. Better drawn here. At the bottom of the page, as we add energy to the chem fields of electrons, they begin to flow in one direction, proportional to the square root of the energy that's been applied to their that's in their chem fields. As they do so, the chem fields generate a magnetic moment that keeps a certain orientation between the electrons. We can measure this with normally with current, because it's the flow of electrons. They're the most mobile charges in a circuit. We measure the current moving around. Important to note, as we've highlighted here, that current is the flow of the charged mass, or the charged matter in a circuit, i.e. electrons moving around. It can be electrons as in electron flow, or it can be conventional flow in the case of positive ions moving around. It is not a measure of the energy in a circuit. The energy in the circuit is the voltage. The current is the flow of the electrons moving in that circuit. In the case of DC current, direct current, the electrons move in one direction. all the time in one direction around the circuit. They're drawn from the negatives and drawn to the positive or the positive charge in the battery or the generator. In the case of alternating current, obviously the positive and negative plates, or in the generator, the positive and negative charges are alternated in a regular pattern every second. This results in energy being applied to the circuit, and the electrons move backwards and forwards as the electrical charge changes in their chem fields. So the electron might have a slight motion, but it tends to be still, and it's the electrical energy that's being transmitted, not the flow of electrons in AC. And again, as we noted in the previous one, you can measure the flow of electrons and count them, the number of electrons per second, or you can relate it back as just an amperage. These are all related through Ohm's law, V equals IR. Again, important to note that the mass of the matter does not change when an electron's in motion. What changes is the energy in its chem field. Obviously we can reorganize this and measure the voltage and the current flow and express it as a form of power. In the case of electrical power, we can express it in these formulations, but we can easily visualize it as the flow of positive and negative energy momenta in a circuit. Once this energy is in the circuit, or the circuit is energized, these energy momenta will induce a motion in the free charge particles in that circuit. They do this by adding some of their energy to the chem fields of the particles in motion. So when a circuit is energized, the electrical energy will flow through the conductors very rapidly, and it will slowly and eventually accelerate free electrons or free charge particles in that conductor to whatever velocity the electrical energy will permit within that circuit. This then explains one of the other mysteries of electricity, and that is drift velocity. When you switch a light bulb on with the switch, the light bulb comes on almost instantaneously at the other end, irrespective of the distance. But the measurements of the motion of the electrons reveals that they move roughly at the speed that you can walk. Obviously the light comes on faster than you can walk to the end of the room. What is happening? What in fact is happening is when you switch the light switch on, the separated dipoles provide an electromotive force and energize the conductor. They form this roadway of divergent and convergent energy momenta along the conductor. Any free electrons in that conductor then begin to accelerate. As they begin to accelerate, they flow, creating a current. In fact, energizing the circuit is already turned the light bulb on. The flow of current is a secondary product, and in fact we'll show further in electrodynamic theory where it is best to avoid current flow wherever possible, because the current flow is actually using up energy to accelerate the electrons, and when you want to stop the electrons, you obviously have to release the energy as heat, and likewise. So flow of current, even though it's a measure of energy within the circuit, is something that should be avoided. We should be aiming to propagate the energy from one point to the other as quickly as possible, which it does naturally, and then prevent current in that circuit, which is just a wasteful use of energy within the circuit. Save all the energy for use at the far end. Obviously we can express volts, which is just a force, as newtons or as volts. They're equivalent to each other. One's an expression of amperage, the other one's an expression of force. They have identical energy momenta, square equilateral geometries within Tetryonics, And in fact, the equilateral geometries obviously explain a lot more than current formulations. We can obviously express Ohm's law in a mnemonic fashion using Tetryonic geometries. V equals IR, where you can see the voltage quickly is just I times R. If you want to calculate for R, you know it's V divided by I. If you're after the current, you can see that it's voltage divided by the resistance. It's a quick and simple mnemonic for Ohm's law. And again, while it's applicable to show the power and the forces, electrical forces in a circuit, we will seek to eliminate the resistance side of things further down the track. So obviously all electrical energies can be shown to be equilateral geometries, and in fact this equilateral energy is everywhere. We are in fact living within an equilateral energy potential right now. We don't notice the potential purely because we have grown up accustomed to the potential that we're within. It's about 100 volts, I think, a meter at the surface of the earth. It varies, but what we should be trying to exploit is the potential difference between different voltage levels to create electrical energy. Obviously we can explain electricity using equilateral geometry now that we've done all the basic foundational electrodynamics, both on the quantum mechanical side of energy itself as well as the electrodynamics as far as accelerating, how we accelerate and inducing acceleration into charged particles. Electricity is just a formal extension of these forces as we sought to tap the forces and use them for our benefit in the way of creating work in one spot and delivering that work to a different spot to be used at that spot. Obviously all energy is shown to be equilateral square geometries of electro and magnetic fields. It's the dipole arrangement of these square equilateral fields that creates positive and negative charges. And again, these charges interact to form electrical fields, as we see here with emfs, where we separate the charges. And we can also create charged matter, as the quantum mechanic lectures have shown. In the case of electrons, we have negative charge matter. They have 12 negative charged geometries with no positives, and they have a total of 1.2 by 10 to the 20 energy quanta or Planck quanta forming their geometries. Where we separate the charges into distinct positive and negative charged geometries with energy, square energy momenta within them, we create divergent and convergent energy fields or voltages. The energy per charged geometry is the voltage. Where we separate them, we have the potential to create a force on charged particles. Obviously, where charges overlap, or charged fields specifically overlap, the charges themselves don't, where the charged fields can be superpositioned, we create a field of force between charged objects that we can exploit to create force in different areas, and we can describe these forces through the familiar law of interaction as expressed by Coulomb and his equations. Obviously, if we connect separated charges with a potential to do work with a conductor, the electrical energy will flow nearly instantaneously between these separated charges in both directions at the same time as they seek equilibrium according to the second law of Tetryonics. And in doing so, they will establish a field of force along the conductor that will create a secondary force on charged particles within that conductor. In this case, in the case of electrons within the conductor, the electrons will be accelerated. They will gain a secondary chem field with square energies again, and these chem fields will have a particular dipole arrangement or magnetic moment. as a result of their motion. The measurement of these electrons with their energy as they go past a particular point per unit of time gives us a measure of current within the circuit. Again, just to highlight geometrically, even if you not only within themselves where we have magnetic fields and electric fields in every energy quanta, if we even create a magnetostatic bar magnet or a dipole, magnetic dipole, and we orientate it by twisting the magnetic dipole back and forth rapidly, we can change the electric field orientation of that dipole, remembering of course that you can't physically detect this field via its electric field properties, but you can detect it where you have a conductor around it, where we allow the flow of electrons between, or we create an electromotive force as a result of these opposite charged fields. The conductor will connect them and will facilitate the flow of electrons within that conductor. Again, same description here. We create an EMF. If you create separated charges, they will create an EMF. Likewise, in the case of bar magnets, there is, although not readily apparent via the block wall, there is a separation, a 0 point where there is no magnetic and there is no electric fields. So there is a separation between the electric and the positive and negative electric fields and the poles of the dipole themselves. It's this quantum separation at the point of singularity that allows us to exploit properties such as induction of current when we move a loop over the magnet. Obviously it connects the energy momenta of the electric fields in such a way that it starts the flow of electrons in one particular direction. Again, this same circuit can be created with a coil of wire, and you can accelerate or place a current in that coil which will accelerate electrons along, and these moving electrons will have a magnetic moment. If you model it using the Tetryonic geometries of particles, charged particles in motion, you'll see that there will be a south-north orientation to the magnetic field that's created through this helical winding, and it's proportional to the number of turns in that winding and or the voltage, the current flow that's created. Again, you can model it with either negative charges in motion, or you can use conventional current with positive charges in motion. The result is the same. Again, reinforcing that Tetryonics explains all the circuital and induced EMF laws that are currently done through left and right hand rules. Again, a little bit chopped off on your page here, but when we separate the charges to create an EMF and then complete the circuit between the charged plates in a battery or in a generator, the EMF will complete the circuit almost instantaneously. It will flow through the wires, with the wires acting as a guide between the positive and negative charges. The voltage of the battery obviously determines the EMF that's available, one and the same, and the voltage will determine the current under Ohm's law in the circuit, and obviously the current is just a measure of the electrons in motion. It's a secondary product, again, as we've stated. The electrical, the flow of electricity will be first. It will be near instantaneous. As the circuit is completed, the light bulb will come on straight away, and then after a moment of time, the energy momenta of the electricity will start accelerating the electrons in the circuit, creating a current. Obviously, when the electrons with their chem fields get to the light bulb, they're slowed down. As they're slowed down, they must release the energy, because the energy is proportional to the velocity. If the velocity decreases, obviously the squared quanta in that same field must reduce in accordance with that geometric relationship. So therefore, that energy has to be given up. The bosons are given up to form photons of light, which we then see emanating from the light bulb. Obviously, just as we did with electricity itself, all this can be described via a cross product of the electric and magnetic fields created by the electricity and the chem fields of the electrons themselves when they start moving. And this is expressed as called the pointing field. It has vectors indicating the direction of energy momenta between the positive and negative sinks and sources, or positive and negative charges on the plates in the battery. And again, the pointing vector is just another representation mathematically of what's represented geometrically using Tetryonic geometry of energy. The electromotive force itself, again, is just the separation of two charged fields, and the voltage of those fields, or the force itself, is a direct measurement of the number of energy quanta, energy momentum quanta, in that charge. These can be different charges. In this case, they're the same charges, 8 volts each, giving us an EMF of 16 volts in total. 8 positive, 8 negative. It's the separation of these charges that creates the EMF, because when you separate them, they then seek equilibrium. You can store this separation in a battery or a capacitor on the charged plates, but when you complete the circuit, the electrical energy will flow almost instantaneously in both directions, noting that the energy momenta is in divergent and convergent directions. Positive will flow to negative, negative will flow to positive within the circuit. But once it's established, the electrons will only flow in one direction, as you'll note here. There is only one direction for the electron flow. The electricity itself is a bidirectional carpet, if you like. That's how I tend to term it. It energizes the circuit and then gives energy to the electrons to create the current flow and the magnetic fields that are created by the electrons as the current flows in the wire. Of course, you can view magnets as an EMF because they have electric fields within their magnetic fields. It's just that the electric fields are neutralized, so they don't tend to be detected, but they are present, as evidence when you slide a conductor back and forth over a bar magnet. The energy momenta of the E fields will create an EMF to drive electrons around in the circuit of the conductor. Likewise, if you separate the charges, you have an EMF. So the geometries of a battery and of a bar magnet are identical. Anything that changes is the closeness of this separation. In a battery, there's a physical separation we can detect. Within a bar magnet, it's a quantum singularity right at the center where the electric and the magnetic fields are zero. It's a singularity, but it is extremely small. There is no, I just hasten to add at this point, there is no fourth or fifth or multiple dimensions past that singularity. The singularity is simply a null point. There is no magnetic and no electric forces at that point. It is the point of crossover for all four, and depending on your motion, it'll be moving from north to south or positive to negative as you cross the point. There is no black hole. It is a singularity in term. It is a null point. Mathematically, this has caused all sorts of trouble with formulating theories of what happens at singularities and the rest. You'll see a lot more discussion on this in the cosmology lectures. In the cases of separated charges, obviously you have sinks and sources. This illustration just goes to greater detail in a larger illustration of the difference between electricity, electron currents, and conventional currents. Obviously, the separated charges have divergent and convergent energy momenta. There are more positive ones in the positive charge, more negative ones in the negative charge field. The separation then creates a situation where they seek to equalize, but the energy is stored, and the amount of energy per charge geometry is the voltage, or the EMF potential that can be created. When the circuit is completed between the two charges, or there is a conductor in place between the two charges, the separated charges under the second law of Tetryonics will seek equilibrium. They do this by both propagating in similar direction, opposite directions through the circuit, and energizing it. If you like, the way I visualize it is they create a carpet of positive and negative energy momenta through the circuit. And if you look at these pictures, you'll see that the positive energy momenta always flow clockwise in the circuit, whereas the negative energy momenta, whether they're on the positive or negative side of the plates, or positive or negative plates, always flow in the anti-clockwise direction. This gives rise to our conventional versus electron flow in circuits. Obviously, in reality, you can measure it either way. One is the equivalent of the other. It's just different charges that you're looking at and different energy momenta that's driving the charges. The reality, though, is that it's the electrons that move in the circuit. It's the electrons we measure because they're the lightest particles. They're in motion well before any positive ions would be in motion. Protons are 2,000 times heavier than the electrons. It takes more energy to move any free protons, and there are a lot more free electrons in a circuit to move because there's more free electrons bound to be broken free in order to move. Chemistry goes into the difference between conductors and insulators. But in this case, the electron flow will be driven by the negative energy momenta, divergent on the negative plate, convergent on the positive plates. So it drives it round anti-clockwise. Similarly, if there was a positive ion free to move, it's the positive energy momenta that would drive it, which again, the positive energy momenta is divergent on the positive plate, convergent on the negative plates. In the circuit, it makes no real difference. What in fact happens is that you will see positive charges going anti-clockwise and negative charges going anti-clockwise, positive charges going clockwise in the circuit. If you were to reverse this circuit to the other side, you would have the opposite direction, obviously. Again, that's what leads to a lot of confusion with motor laws and the rest. It's the direction, it's the chirality of the EM fields and the energy against their direction of motion and the direction of the circuit itself that creates the flow that determines the eventual magnetic orientations within that circuit, and it creates a lot of confusion. A lot of that's removed using Tetryonic geometries because, as I said, you can quickly map the direction of the particle, the direction of the EM forces, and the magnetic moment that's created for whichever type of particle you wish to map, versus using all the hand rules to figure it out. Again, illustrating the same thing from a different perspective. This time I've highlighted the magic carpet effect, as I've said. Between a positive and a negative charged surface, when you apply a conductor, there will be a flow of electrical energy. And this circuit I like because it clearly shows what's going on. The electrical energy momenta flows instantaneously. If you look at the positive charge, you can see that it's divergent negative energy momenta with convergent positive energy momenta. At the positive end, you see that it's divergent positive with convergent negative. It's the same energy, different charges, But when the circuit is complete, it all forms the same thing, which is electrical energy in the circuit. The circuit is energized. The conductor is alive with electrical energy. There then are free particles. In most cases they're electrons. You can model it as the opposite in the case of conventional current flow. It's a historical quirk. Benjamin Franklin tossed a coin as to which was positive and which was negative, what was flowing, whether it was positive charges or negative, and he chose the positives flowing when in fact it was the opposite direction. Don't hold it against him. They can both be explained, they can both be modelled. It's just that from a physical perspective, it's best to know that it's the electrons in motion, not the protons. In this case we have positrons and electrons in the circuit. Obviously it must be an antimatter circuit as an equivalent. And in this case, irrespective of whether it's a matter or an antimatter circuit, this galaxy or another, the electrical energy will flow. So in the antimatter alien's homeworld, he switches on the light bulb and it still works. In his case, it will be positrons flowing. Our case, it's electrons. The electricity in both cases is identical. It forms a energized carpet on which charged particles are accelerated according to their charge. As these particles are accelerated, obviously their chem field has to increase accordingly in proportion to their velocity. It's the chem field that changes because the matter, or the charge geometry of the particle, the matter itself, is velocity invariant. It does not change. All the mass energy from motion is in the chem field itself. Obviously, it accelerates when we switch on the circuit. The light bulb comes on straight away as it releases some of this energy at the far end. But eventually, these charged particles will be accelerated, and we'll detect a current flow, and some of the energy will drop down because some of the energy is going into moving these electrons along. Obviously, where the electrons get to the light at the other end, they'll slow down because of the resistance, and they'll lose some of this energy as light, or particularly as heat, which is what we want to try and avoid. We want the electrical energy to get to the end and radiate as light. We don't particularly want energy being used to move charged particles along the conductor. And again, obviously, depending on your arrangement of your EMF of your charged plates to create the voltages, depending on the arrangement of these dipoles, affects the direction of current flow. Positive charges move one direction, negative charges move the other. And changing the voltages, or the dipole voltages, in a circuit will result in a change of the current flow, which is how AC electricity comes along. DC, the dipole remains in one spot and the current flows in one direction, or the electrons flow in one direction. In AC, as they begin to move, the dipole is changed rapidly per second, and the electrons reverse direction and stop. What this then does is it prevents the build-up of, or wasteful build-up of, energy in moving electrons through a circuit, and facilitates the flow of the establishment of an energized circuit where the energy is present, but it's not being wasted not wasted greatly, trying to move electrons from one dipole to the other, or one voltage to the other. The electrons tend to remain still, oscillating backwards and forwards, while the electrical energy is present right along the energized circuit. Obviously, as the electrons move around the circuit, they have their kinetic energies. If you place a electron in a circuit, if it's a generator or even a battery, as it enters the circuit, the voltage, or the EMF, will accelerate it, and it will gain energy in its chem field. In the case of 1 volt, a 1 electron volt one electron volt kinetic energies, or chem field, energy in the chem field is added to the electron to give it motion around the circuit. And again, it always moves according to the energy momentum of the charge or the EMF that's energizing the circuit. These can all be re-expressed using our familiar formulas. Where we're expressing for kinetic energy, obviously it's half of the field created by the matter by the velocity squared. Remembering it's matter by velocity, not mass. It is still the mass of the matter, but it's better to say matter velocity squared because it is the electron in motion that you're measuring. And those units are obviously what's used in modern particle accelerators, hence why you'll see electron volts in a lot of physics measurements. Again, straight out of electrodynamics, more detail of this is available in the spectral line discussions and lectures and in QED handbook itself. Any electron in motion will have its chem field, obviously, square energy quanta. Half of that energy, as discussed here, half mv squared, is the kinetic energy, as it's formally called. The other half is the magnetic moment. They're equal to each other, and together they form the chem field of particles in motion. The charged electrons are matter particles. They're 12 pi energy geometries. So they're measured per c squared, c to the fourth. The energy itself is mass energy, so it would be n pi m alpha nu squared, or 12 pi energy. Get it straight. It will be n pi energies for the chem energy, mass energies. Per unit of time, the energy becomes mass. So you can say it's a mass energy equivalence. They are a two-dimensional field, the chem energies, so they're not normally detectable. However, the energy momenta produce a linear force, as we've discussed, and this is what creates Coulomb's law. As the electron speeds up or slows down, obviously the energy content changes, as highlighted here with the quantum levels, and it adds or releases bosons, which create the familiar spectral lines and or white light, incandescent light in light bulbs. All the energy that's normally released in a light bulb is the result of changes of kinetic velocity of charged particles and the release of energy from their chem fields. This is illustrated here with the differing velocities and energies of electrons. As it accelerates, the energy has to be increased in accordance with the square of the velocity. And obviously, with the square of the velocity comes an ever-increasing magnetic moment and increasing kinetic energy as a result of its motion. As we highlighted on the previous page, these are all matter velocity squared relationships, or mass matter velocity squared. They can be also re-expressed as quantized energy, or Planck's constant by the quanta squared for the geometry, half of which could be either magnetic or electric. And again, as they're all mass energy or 2D fields, they are all measured per c squared, or energy measurements per c squared, to give us mass. Obviously we can, now that we know the geometry and the quantization of the energy, we can solve for a number of things. We can divide the chem fields by the Planck's constant to give us how many squared quanta, or the frequency, or the quanta themselves. Whether we're measuring, in the case of quanta, we're measuring bosons or charge or quantum levels. Frequency, we're measuring the photons that are in there. Quanta, we're measuring the discrete energy quanta that make up that energy field, in which case it would be a squared quanta within that field for the entire field. We can measure, divide by the momentum of the field and solve for the wavelengths. We can alternatively use the measurements of the momentum that's created by the field, divide it by, or quantize it, and calculate wave numbers for the photons in the field. There are a number of ways. Spectral lines in QED goes into this much greater detail. Obviously, chem fields are single pi geometries, charged geometries, or they can be re-expressed as 4 pi geometries, where you're referring to discrete electromagnetic field properties, positive and negative versus north and south. They can be a 4 pi geometry of energy. But again, as noted here at the middle of the page, the chem field stores all the mass energy of motion. So you take the total mass energies of a particle in motion, take away its rest matter, which is a standing wave of mass, or mass energy in a standing wave geometry, and all the energy of motion is stored in the chem field. The matter itself is Lorentz invariant. The final thing that Maxwell added to his equations was a term for displacement current. Looking at the flow of electrical energy in a circuit, obviously where electrons encounter a capacitor or similar, the electrons themselves don't flow through. The capacitor will block the DC current flow, but will allow an AC current flow through the capacitor. It does this by storing the energy as a charge between the capacitive plates, and then using this charge similar to EMF to accelerate electrons on either side of the plate. Obviously, as illustrated here, the electron will flow in a circuit depending on the oscillation of the circuit, of course, but it delivers its energy. When it encounters the plate, whichever charge it is, it stops. If it's attracted, say, a positive plate, it will stop here, but its kinetic EM energy must be released. Obviously, the electron has stopped. It has gone from a set velocity to 0, so all this energy, whatever the energy was from its velocity in motion, its drift velocity, must be released at this point of stopping. It does so, and the KEM energy becomes a charge on the plate. Obviously, all square energy levels are bosons, odd-numbered charge geometries. These then form up on the plate to create a charge or a voltage in the capacitor. The charge on the plates separated is what creates the voltage. The capacitors themselves are made by having separated plates of metal separated by a dielectric. Large plates, the larger the plate, the more charge they can hold, obviously. These plates are then wound up tightly to form the little cap structures that you see now in most modern electronics. They can be solid, different formations, but that's the classical way of creating a capacitor. 2 charge plates separated by something, a spacing, a dielectric that doesn't normally allow the current flow to go through. So you get a build-up of charge on the plates due to electrons stopping and giving up their chem energies. These then form a potential on each plate which is separated, and that separation of charges can be used as an electromotive force to drive current, or that can energize the circuit or drive electrons in that energized circuit around the circuit. But they prevent the flow of electron. It's a physical barrier to electrons. They cannot flow where there is no conductor. So they just stack up, and then the current's reversed, the voltage is reversed, and they flow the other way. The capacitor charges and discharges and charges and discharges. You can obviously disconnect the capacitor once it's charged, and it will store the charge. Or alternatively, it'll act like a battery in that case. When you close the circuit with something else, it will discharge, with creating electromotive force and energizing the circuit in the conductor that completes the circuit. In the case of what's the best way to describe this? In the case of displacement current, what happens is the charge will build up on the plates in the circuit, or between 2 plates, wherever charge builds up, to the point where eventually the electrical charge will reach out and try and complete a circuit by itself. It will grow, the voltage will increase as the energy momenta within the charge geometry increases, to the point where it eventually will have sufficient energy momenta to reach out across an empty space or an open space and to discharge against another plate or another circuit. This is normally an explosive discharge of energy, normally lethal, and normally it's a way it can be best described as lightning. It's a explosive discharge, an arc between the two, between the plate that has the charge and the plate that's providing the grounding or completing the circuit. And it's an add-on to Maxwell's equations by Maxwell, as he sought to explain how this energy is stored up and then released. He saw it as the compression of an elastic medium. In some respects, they are storing energy momenta, equilateral geometries compressively within the charge geometry. So in that respect, he's right. However, the equilateral geometry is the key part with Tetryonics, as it allows us to create diagrams such as this and explain the flow of electrical energy versus the flow of current and chem energies. Again, electromagnetic induction is just the coupling of the energy in one circuit to another circuit, usually via a conductive loop or some other similar fashion. We'll have square energy or equilateral energies stored in one circuit, and where a secondary circuit is superimposed or allowed to interact with the first circuit, again following the second law of Tetryonics, energy will seek to equalize and it will be spread out between the two circuits. They will share the energies and a current flow will be established in the second circuit. A lot of these, or all of these inductions are the result of the motion of bosons, be it in this case a single boson of 1 pi or any other boson that has odd number of charged geometries. The bosons themselves conduct the electromagnetic charges between the coupled circuits. These can then obviously combine in the circuit to form photons. The square energy fields of electrons in motion, where the force is pushing the electron, the electromotive force moves the electron, creating a chem energy of square energy momenta. Also, these square energy momenta contain odd-numbered bosons. These odd-numbered bosons can obviously form photons, where they're released as differences in energy due to the differences in velocity, or where energy is just released in a circuit. They will release it as bosons that then couple to form photons. As illustrated at the bottom here, you can couple two W bosons, a positive boson, W boson at the top there, with a negative W boson, and they will form photons of energy. They're released as charged bosons, but they couple via the weak force to form photons of electromagnetic energy propagating in two directions. Obviously, again, the energy within a circuit will accelerate electrons, and the energy of that force that is accelerating them will be stored in the chem fields of the electrons in motion. If the velocity changes, the energy within that chem field must change in accordance with E equals mv squared, and in doing so it must release, or if the velocity increases, it must have additional energy put into it in the form of bosons. Obviously, these chem fields extend out from the charged objects just as electrostatic fields do, and using Tetryonics with the chem fields, we can in fact we can explain Coulombic forces that cannot be explained using Coulomb's rule or Ampere's law. We show the magnetic, in the first illustration here, we show the chem field of two particles in motion. We show the dipole arrangements of those chem fields, and we show that they will have an attraction between similar charges moving in the same direction will have experienced an attractive force. In the case of, if these were two negatives, there would be a repulsive force between the two particles, because they'd be if there were two similar charged particles, there would be a south-north, south-north, so it would be attractive because they're moving in the same direction. If they were opposite charged particles moving in the same direction, for example, a positron, an electron, you'd have a north-south, south-north, so there'd be a repulsive force between the particles. Similarly, even though neutrons are neutral particles, they still are consisted or created from charged geometries, and these charges will bring the particles together via their residual electric force. And the particles, when they form, obviously in this case a neutral particle has been attracted to a negative via the opposite charges. When they form, they will also have in this case a electrostatic field, or they can have a chem field resulting from from the particle's motion through space, where the kinetic energy is stored in the field. In either case, we will have north and south poles. In the case of particles that come together, differing particles like this, their differing chem fields can also create, or will create, the nuclear magneton. A lot of this is much better explained in Tetryonic chemistry. Obviously, it's the superpositioning, as indicated up on the top right-hand illustration. It's the superpositioning of chem fields and electrostatic fields of particles. The energy momenta of these superpositioned fields is what creates the Coulombic attraction between particles. In the case of protons and electrons, they're attracted together. In the case of a proton and a positron, they would be repelled. Tetryonics explains all of this through superpositioned energy fields. Obviously, Coulomb's law is just an example of superpositioned energy fields, as we've touched on earlier, where the energy momenta on the superposition field repels or attracts makes no difference. It's just a change of the vector of force. But we can measure the energy, the force that each field produces on the other through its individual energy momenta in the form of Newton meters for each field, giving us Newton meters squared for both. And that's again directly related to the inverse of the square of the distance. So it's Newton meters squared per distance squared, or per r squared. That's how we generate the Coulombic force constant. We simply measure the energy momenta, divergent and convergent energy momenta, between differing charges. And of course this gives us our law of interaction as well. We can utilize these forces in the charged fields as a result of their energy momenta to give us forces or forces firstly generated by particles in motion in conductors. As you can see here, again we've modelled the chem fields of charged particles in motion in a conductor. Won't go into great detail here. Obviously the particles are moving one direction or the other by whether there's a circular drawing, or the point of the arrow, or the tail of the arrow, X's or dots on the conductor. You can see the north field, or the north-south, south-north dipole arrangement of an electron. In both cases, depends on their direction of the electron and its motion in the conductor. If they're moving in opposite directions, there's a repulsive force between the dipoles of the chem fields. If they're moving in the same direction, it becomes an attractive force between the dipoles of the chem fields. In the case of opposite charges, where we have positrons and electrons in motion, we can model them as well, and we can show against the standard drawings of lines of force, magnetic lines of force, the chem dipoles, and we can show the repulsion between opposite charges and moving in the same direction versus the attractive force, magnetic force, between opposite charges moving in the same direction. Opposite directions, sorry. It gets very confusing to explain all the permutations of these directions. Obviously, again, as we've illustrated here, we can simplify it back to just using straightforward equilateral triangles highlighting the magnetic moments, and instead of drawing all these detailed diagrams and trying to remember which directions to which, we simply follow the direction that the equilateral triangle is pointing us, and we know what charge the particle is by whether it's a positive or negative charge E field. So all these complex drawings and mapping of magnetic forces resolve back down to simple equilateral geometries. Of course, we can continue this for charges moving in a circuit to charges moving within a magnetic field. And as I touched on earlier, the magnetic dipoles are separated on either side of the EM field, and when they move through a magnetic field, an external magnetic field, this will create a torque similar to the wings on an aeroplane. It will create a magnetic torque on the EM field or the chem field. Again, the chem field surrounds the particle, so if the chem field is torqued, the particle itself will experience a torque, and this creates the familiar curved tracks of particles within external fields in, say, mass spectrometers or within the Large Hadron Collider or other particle accelerators like that. It's expressed mathematically as the Lorentz force with its vector equations for the electric charge versus the velocity by the magnetic force on the particle. We can simply redraw it with equilateral geometries, and in doing, we also get rid of the hand rules to describe the force that's experienced. We can simply interpret it straight off the equilateral geometries here. And obviously, if you were to inject a particle into a strong enough charge field, it would go in a circular motion, and that's what happens at CERN in the Large Hadron Collider. The magnetic field steers the charged particle by its chem field, by bending the dipole on the chem field. It torques it into a circular motion, which then continues around and around. And as you add more energy to the particle, or to the particle's chem field, obviously the velocity has to increase, because the square of the energy equals the velocity, and the linear momentum is just the square root of the energy. So as you add more energy, the particle will accelerate in a circular fashion due to the magnetic field, and it will continue until, in the case of CERN, you redirect it via altering the magnetic field so that it collides with another particle. Again, we can map differing helical windings of inductors along with different directions of current flow in those inductors, and model that using Tetryonic geometries to explain all the different right and left hand rules that are normally applied to figuring these things out. Feel free to wander through this illustration and test it for yourself. You'll see that it does work. Compare it with the traditional wrapping of fingers around the inductor or the conductor, and you'll see that it all still tallies up exactly as it would. One of the other things that comes up in electricity is a thing called the skin effect. When DC current flow goes through a conductor, or direct current, the electrons flow in one direction from positive to negative only. A huge current can be flowed through the conductor. Obviously, once the electric field is established between the dipoles, we can then allow the electrons to move over time, creating the current. They will have their own chem fields, and as you can see here in a exaggerated picture of what's going on, the electrons' chem fields will all be north-south orientations, allowing a tight packing of the electrons within the conductor itself, allowing a lot of them to pass through. If, however, we apply AC to the same conductor, and obviously in doing so we alternate the dipole or the electromotive forces, what happens is the electrons will move in one direction first, then they'll turn around to move back in the other in accordance with the rapid oscillation of the dipole. As the electron or the charged particle changes direction, obviously its chem field changes direction as well, and in doing so you create a region within the conductor where electrons can't flow. And this is created because the chem field's magnetic dipoles, when they alternate, create a repulsive section within the center of the conductor, which then causes the electrons to bunch up on the outside, hence the name skin effect. The core of the conductor is left relatively free, and all the electron or the current flow is along the outside of the conductor. When you go back to DC, obviously you can carry more current. Tetryonics, through this illustration, clearly explains the physical mechanism behind the skin effect. Again, all the algebra that you find in electrical books and in electrodynamics can be quickly resolved using Tetryonic geometries for energy, whether it's light or electricity, charges, EMFs, anything. We can quickly break them back down into the basic math, and we can show the geometry that gives us the math. A lot of people refer to math being the language of physics. If that's the case, obviously, again, the geometry is the grammar for that math, for that language. The mathematics that has been derived to describe everything that is going on in physics is nothing more than a language used to describe the equilateral geometry of energy. Obviously, in the case of photons, we can explain a lot more. In this case, we'll finish up at this point, and I'll explain photons at a later time.